Good morning, Amherst. Monday, May 18th, 2020. It's time to start electrochemistry, so we've got a new packet here. All right. This promises to be a somewhat lengthy video. There's a lot to memorize or a couple processes, but I'm going to do what I can in terms of writing here, although I will tell you that it's going to be a little bit difficult in terms of trying to fit it all on the page, so bear with me. So, the electrochemistry unit you can think of as applied redox. Basically, you're doing redox reactions to generate electricity and use that, or you can use electricity to do some redox chemistry that wouldn't happen by itself normally. So, think of electrochem as applied redox, and we're going to start with electrochemical cells. They're broken down into two basic categories. You've got Voltaic cells, which you might refer to commonly as batteries, and then you've got electrolytic cells, which are actually kind of the exact opposite. So the big picture here is in a voltaic cell, you're taking chemical energy, potential energy, and you're using it to make electricity. You're turning chemical energy into electrical energy. In a voltaic process, you're using electricity to do chemistry that wouldn't happen spontaneously. So voltaic chemical energy gets turned into electrical energy. In electrolytic, electrical energy gets turned into chemical energy. So voltaic cells are spontaneous, electrolytic cells are not spontaneous. You're going to generate positive voltage in a battery. Okay, I know it's kind of weird with spontaneous. We said negative delta G, but for voltage, it's positive, whereas an electrolytic cell, it's going to be negative voltage. The basic diagrams are going to look a little bit different. In the diagram you're going to see for a voltaic cell, you're going to see two beakers, a couple electrodes, a salt bridge in the middle, and a voltmeter. In an electrolytic cell, you're going to see a power source, and that's a dead giveaway. This doesn't happen spontaneously. You need to make it happen. So you could use a voltaic cell as a power source to make an electrolytic process happen. But galvanic cells or batteries, they are a power source, whereas electrolytic cells, they actually need a power source. So they're pretty easy to recognize the difference. If you see a power source, that is definitely electrolytic. Now, we're going to be using supplemental table 6 a lot. Now, you could say what you want about standards in education, but this is what the electrochemistry table looked like when I took chemistry in high school. And this is table J, and this is what it looks like today. Okay? So much for raising standards. In any event, the ACS and the Amherst High School Honors Chemistry unit, we still include things like voltage. Now, a couple things you need to know about table 6 here. First thing, the ionic concentrations, every solution is going to be 1 molar. You're going to be at standard lab conditions, 298 K, 25 degrees Celsius in 1 atmosphere. But every half reaction here is written as a reduction. You see that? Everybody's gaining electrons. There is no such thing as a reduction reaction. One of them has to become an oxidation. To make any of these oxidation, you simply make the products or reactants and flip them around, and you change the sign on the voltage. Not a big deal. The other thing you're going to note about this table is that smack dab in the middle, you'll notice up top these are positive voltages, down below these are negative voltages, but right dab in the middle there's this 0.00 for hydrogen. 2 hydrogen ions gaining 2 electrons become hydrogen gas. That's the arbitrary standard against which all other half reactions are measured. It's basically you have an acidic solution and you put electricity into it until you can get hydrogen gas to bubble off under those conditions, and you call that zero. Basically you tear the machine. So all of them are measured against them. They call that 0 volts. It's an arbitrary standard. Okay, that shows up from time to time. Think about this. Sea level is an arbitrary standard. If I call this level 0 feet above sea level, it's the sea level. Here's your water. Okay, and I know that Buffalo is roughly, let's say, 500 feet above sea level. And I know that Denver is roughly 5,000 feet above sea level. Then I know by difference, without having to measure it directly, that the difference between Buffalo and Denver should be about 4,500 feet, because I measured them both against some arbitrary standard. That's what you're doing here with establishing the hydrogen half cell to be 0. You're making a baseline, measuring half reactions against it, and then through analogy or through logic, if A then B, if B then C, therefore if A then C, what is it, syllogism they call it, then you can figure out the potential energy difference between two dissimilar metals without having to measure it directly. Okay, this starts in the 1700s with Luigi Galvani. He basically takes a piece of zinc and a piece of copper and he touches them to a dead frog's leg and the leg moves. Okay? It's pretty crazy stuff, but basically you take a dead frog and you could create animal electricity from it. Immediately thereafter, a guy by the name of Alessandro Volta said, I don't need the frog, I just need an electrolyte in between them. Basically, I can get electricity to flow in between two different metals as long as there's a solution that will conduct that electricity. So what was the galvanic cell became the voltaic cell. And in the early 1800s, a British guy by the name of John Frederick Daniell, he used copper and zinc with copper sulfate, copper 2 sulfate, and zinc sulfate, and he created his Daniell cell. It's just an example. So the Daniell cell, the voltaic cell, the galvanic cell, these are all batteries, if you will. These are all things that generate electric current from having two dissimilar metals connected by an electrolyte. For all you Breaking Bad fans, if you remember when Jesse and Mr. White got stuck in the desert in the mobile home, they were actually able to create their own voltaic cell from a bunch of nuts and bolts and some solution he had and a sponge. Alright, this is where my paper is going to get a little bit screwy. I'm going to have to go sideways here. And I'm going to slide my camera up because, well, I don't even know if we'll be able to fit both. But here we go. So in any of these voltaic cells, we're just going to use voltaic as the generic term. The first thing you need to know is that the anode is the piece of metal that is the more reactive of the two. Table J is easier in this regard to just figure out, like, okay, if Danielle was using zinc and copper, I can go to table J and I can say, all right, there's zinc and there's copper. Zinc is more active than copper. Zinc is going to be my anode. Copper is going to be my cathode. The more reactive metal is called the anode. The less reactive metal is called the cathode. Anox, red cat. Oxidation occurs at the anode. You're going to have to flip the reaction for the anode from table 6. These are all written as reductions. You're going to flip that one. The cathode, you're just going to copy it as you see it. So the anode is where oxidation occurs. The cathode is where reduction occurs. Reduction occurs at the cathode. Mr. Bauer told me seduction occurs at the cat house. I'm just going to take his word for it. All right, so connecting those two pieces of metal, you're going to need some wire, and the wire is what allows the electrons to flow. The electrons always go from anode. Oxidation's occurring there. You're losing electrons. They're going somewhere. They're going through the wire. And they go to the cathode. You put your device in between, whether it be your cell phone, whether it be your flashlight, but you could also put what's called a voltmeter in between to measure the potential energy difference in between those two. So the basic idea for the Daniell cell is you've got some zinc and you've got some zinc ions, you've got some copper ions and you've got some copper, and they're separated into two beakers, and this is kind of standard notation here. This would be the anode, where you can see zinc 0 is turning into zinc plus 2, and this is the cathode, where copper plus 2 is turning into copper. So you've got a beaker here, a beaker here. You've got this thing called a salt bridge in the middle. We'll get to that in a minute. You've got a piece of metal, you got a piece of metal, you got some wire, you got your voltmeter, okay? It doesn't matter which you make, anode or cathode, just understand that whatever one you call the anode, the electrons are going from anode to cathode. It doesn't have to be left to right. You can always reverse those. I can turn that thing around and look at it from the other side. All right, so in this case, here's a piece of zinc. Here's a piece of copper. Those are free elements, 0, oxidation state. In solution, I need some zinc ions on this side, and I need some copper ions on this side. Now, you can't go to the shelf and, grab me a bottle of zinc ions, but you can grab a bottle of zinc sulfate or zinc nitrate. Same thing with copper. I'm pretty sure Danielle used sulfates for both of them, but it could be anything. They call that a spectator ion. I'm just going to call it X minus. It could be sulfate, it could be nitrate. It doesn't matter. The concentration of the spectator ions is never going to change. They are just there to maintain the neutrality of the solutions. So you've got your solution here, your anode, your cathode, your wire, your voltmeter, and your salt bridge. This is the basic diagram for any voltaic cell. The Daniell cell is with zinc and copper. So let's talk about the salt bridge. What's its purpose? Well, basically, salt, made of ions, so it's an aqueous solution of ions. It's an electrolyte, and it completes the circuit. Circuit means circle. The electrons are going one way, and if they don't have the opportunity to come back, or charge doesn't have the opportunity to come back, you don't have a complete circuit, and you're not going to get any power out of it. How do they do this? They maintain the neutrality of the solutions. So you had your solutions here, and you've got all these positive and negative ions in here, and I'm oxidizing here, and I'm putting all these zinc positive ions into solution here. And over here, my electrons are going this way from anode to cathode. They end up here. And these copper +2 ions end up grabbing those electrons and depositing on the surface here. Well, I'm getting extra positive ions in this solution, and I'm losing positive ions in this solution. At the end of the salt bridge, you've got a semi-permeable membrane, basically like a piece of cotton. And you've got extra ions in here. Well, if you've got positive ions coming in here, I can send some negative ions in there to balance it out. Keep the solution neutral. If I'm losing positive ions, I can send some positive ions here to replace them. I've got a gajillion ions up in my salt bridge. That's an oversimplification. The ions can go both ways, but for our purposes, that's what we're going to say. So basically, the salt bridge allows ions to flow. The wire allows electrons to flow. The salt bridge allows ions to flow. The spectator ions that are in solution, they're not involved in the redox reaction. The concentration of the spectator ions throughout the whole process remains the same. So the sulfates in this case, they don't change. Could have been 2 nitrates. You get the whole idea. All right. So here we go. Here's your, I'm moving to pencil now because it's hard to write with marker on these papers, but here's your electrode, here are the corresponding ions, here are the corresponding ions, here's your voltmeter, here's your wire, here's your electrolytic solution, that's your salt bridge. You could use something like sodium nitrate, you can use anything, just make sure that it's not going to form a precipitate on the other side. It could be sodium chloride, could be whatever you like. All right, you put a semi-permeable membrane in the end, it lets ions through both ways, but it doesn't let the solutions mix directly. So you just take some cotton and stuff it into the end of this U-tube. Yes, they really call it a U-tube. So you fill that U-tube up with salt water, stuff some cotton in the end, and you're good to go. So here's our Daniell cell. You've got zinc over here, you've got copper over here, you've got zinc ions there, you've got copper ions there, you've got your electrolyte in here, you got your voltmeter, you got your wires. Okay, it's the basic diagram. It's always going to look like that. Zinc is more active than copper in table J, so that's going to be my anode. And copper is going to be my cathode. So this is my cathode, this is my anode. The electrons are always going to go anode to cathode. And the anode was more active, the cathode was less active. You can use table J for that, it's a little easier. Oxidation is going to occur at the anode, reduction is going to occur at the cathode. Anox, red cat, always. So I'm going to go to supplemental table 6. These are all reductions. Let's do the reduction first. I'm going to find copper +2. There it is. Hope you can see that. Copper +2 electrons goes to copper solid, which means 0. That's positive 0.34 volts. That half reaction is positive 0.34 volts. Now I need the half reaction with zinc. And if I look on table 6 here, the zinc reaction is right here. Zinc +2 electrons goes to zinc 0, and that's negative 0.76 volts. However, I can't have reduction, so I'm going to flip this one. Reactants become products become reactants. Zinc 0 goes to zinc +2 and 2 electrons. The negative voltage becomes positive voltage. So when you flip a half reaction, change the sign of the voltage. Now if I put those together, I hope you can see this. Copper +2 electrons goes to copper 0, positive 0.34 volts. Zinc 0 goes to zinc +2 and 2 electrons, positive 0.76 volts. 2 electrons here, 2 electrons there. Copper +2 plus zinc 0 goes to copper 0, zinc +2. You get 1.10 volts out of that battery. That's the maximum amount you're going to get out of that half cell at standard conditions. 1 molar concentrations, 298 K, 1 atmosphere. Now, of special note, if the electrons lost don't equal Electrons gained. We know that that doesn't work. You multiply your half reactions accordingly. But, this is a huge but, never multiply voltages. Never multiply the volts. Voltage is a measure of potential energy. So, where my pencil is right now, to the table, that was a loss of potential energy. If I have two pencils there, and I drop them, I didn't change the height. I didn't change the relative potential energy of either of them. The number of electrons does not change the potential energy difference between the two metals. So if this was 2 electrons and this was 3 electrons, I would do the 3-2 cross thing, get them both to be 6, but these numbers would remain the same. The numbers for the voltages remain the same. It worked out pretty well here. We had 2 electrons gained here and 2 electrons lost there, so I have a net ionic reaction. Now here's an important point. When I have my net ionic equation, I use up reactants and I form products. Over time, I'm going to be using these up. These are going to decrease. These are going to increase. My voltage, what happens to a battery over time? It gets weaker and weaker and weaker and weaker. Look at your cell phone. Oh, I'm at 89%. An hour later, oh, I'm at 72%. You're getting less and less voltage out of it. So the copper plus 2 ion concentration is going to decrease. The amount of zinc you have is going to decrease. The amount of copper you have is going to increase, and the zinc plus 2 ion concentration is going to increase. This is an important thing here. The things on the left are going to decrease, the things on the right are going to increase, and remember, this is the maximum voltage you're going to get. The initial voltage is going to decrease over time. So here we go. Here's your zinc. They're going to lose some electrons. They're going up the wire to the cathode. From anode to cathode, the zinc ions are going into solution. These electrons go this way, they go through the voltmeter, they do the work they're supposed to do, they deposit on the end of the cathode over here. The cathode has all these negative electrons. Have you ever seen a Van de Graaff generator? You put your hand on it, it makes your hair stand on end. That's basically what's happening. It's putting electrons into you. Electrons don't like each other, they're negative, they go to the ends of your hair, they make your hair separate and stand on end. Well, the copper plus 2 ions in solution find these electrons remarkably attractive, say, hey, I'm a very eligible positive 2 ion. Here's some negative ions or negative electrons over there. Positive charge likes negative charge. So these ions migrate over and they deposit on the surface of the cathode. That's why this is getting heavier. Meanwhile, the anode, they're losing electrons. They're going into solution. This is starting to look like Swiss cheese. It's oxidizing away. It's corroding, if you will. Now, this is all good and well. It's going to happen for about a split second, at which point this solution is going to get flooded with zinc plus 2 ions and have a net positive charge. And this solution is going to have a deficit of positive charge. And the cell is going to say, that's it. I'm not sending any more electrons over. There's not enough energy to be had. There's not enough driving force. Enter the salt bridge. You've got a reservoir of ions here. The solution over here has some excess positives, so the salt bridge says, send some of my negatives over there to neutralize it out. Negative ions are anions. Anions will flow toward the anode. Over here, you're losing your positive ions at the cathode. So cations, positive ions, are going to flow through the salt bridge, through the membrane, and they're going to flow toward the cathode. Anions go toward the anode. Cations go toward the cathode. That's an oversimplification. Okay, there's more going on there, but for our purposes, that's what we're going to say. Anions go toward the anode. Cations go toward the cathode. Here's my oxidation half reaction. Here's my reduction. So the anode's getting oxidized. It's starting to look like Swiss cheese. It's corroding away. And the cathode is starting to look brand spanking new because it keeps getting coated with brand new atoms of freshly formed copper. Okay, so over time, the anode is going to lose mass. The cathode is going to gain mass. This is corroding away. This is getting coated. All right, these are getting, ions in solution are increasing. And over here, these are getting used up. The ions in solution are decreasing. When you get to equilibrium, when the forward reaction rate and the reverse reaction rate equal each other, you're down to 0 volts and you have a dead battery. All right, so that's the basic idea with a voltaic cell. So if I go to my packet, come on, let's zoom down. There's some definition stuff up here. Here's my Daniell cell. Okay, this is more reactive. This is my anode. This is less reactive. This is my cathode. Anox. Red cat. This is oxidation. This is reduction. My net ionic equation, if I add those together, is I have zinc 0 plus Cu plus 2 goes to Zn plus 2 plus Cu 0. I look up my voltages. The zinc over here, I had to flip, so this was positive 0.76. This was positive 0.34. This is a total of positive 1.10 volts maximum. If you're doing this and you end up with a negative voltage for your addition, you have your anode and your cathode upside down. You've got them backwards. So positive volts will tell you, yes, that's a voltaic cell. You've done it correctly. So they ask you to go through the Daniell cell here, labeling a galvanic cell, but it's a Daniell cell. It's zinc and copper. Okay, so you're going to do this one for homework, and then you're going to do this one for homework. Okay, so you've got aluminum and lead. I want you to answer these questions, and I want you to label up your diagram. And same thing here. You've got lead and silver. I want you to answer the questions, label up your diagram. All right? We will go over those two tomorrow. So you're going to review the Daniell cell. You're going to answer the questions on it. You're going to review another voltaic cell, this one between aluminum and lead. Answer the questions on it, determine the voltage, label the diagram. You're going to do the voltaic cell between lead and silver, answer the questions, label up the diagram. We'll pick it up here tomorrow.